Okay, we'll continue our lecture. So the most common supports that we'll encounter in this course is the fixed support, right? The fixed, the pin, and the roller. Okay, so as I have said that we can describe these supports in terms of forces and displacements. But for now, let's draw the symbol for fix. So the symbol for fix is that we have this kind of figures, and for pin, we have this something like this, right? This is our member, and this is the support. And for roller, it's something like a pin, except that it has rollers. And for some text, it uses a circle rather than this pin with rollers. Anyways, the main idea is that uh, the main idea is all about the support reactions and the displacements. Okay, so in terms of support reactions, and in terms of displacements, so when I say displacements, that could be linear displacements or rotational rotational displacements. Okay, so for this fixed support, we have forces along x, right? So we have forces along x. Okay, so let's write our UZS here. So this is our x, this is our y. So that means we have forces along x. So we have Rx, we have also reactions along y, and we have reactions, a moment reactions along the z-axis. Okay, so meaning that the three forces are present for a fixed support. Okay, so what does that mean is that these three forces prevents this member in moving along x or moving along y or even rotating. Okay, so therefore, in terms of displacements, or let's just write degrees of freedom, in terms of motion, this has zero motion. So it cannot move along x, cannot move along y, and cannot rotate along the z-axis. Okay, so for a pin, we have only two reactions. So we have R sub y and R sub x. Okay, so these two reactions, that means that in terms of displacements, it can rotate. It is allowed to rotate. So this is how many displacements? Then it has one. Okay, one rotation along the z axis. And for the roller, we only have one. And take note, this one reaction is perpendicular or normal to this surface. Okay, so that means that this roller is free to move along x, and it's also free to move. I mean, the member is free to move along x, and the member is free to rotate along the z-axis. So that means this has two degrees of freedom. Okay, so where do we find this fixed support, the spin support, or the roller support? Okay, so for the fixed support, typical is, for example, a base plate of a steel column. Okay, so the base plate. So, for example, we have a plate, a bearing plate, and then it's bolted on a pedestal. Okay, so this can be modeled as a fixed, or the reinforced concrete beam and reinforced concrete columns, right? So they can be modeled, or they are usually modeled as fixed support, right? Fixed support. But for pin, it means that it allows rotation. And by the way, the rotation does not necessarily mean like it has to rotate very significant. I mean, very directly. I mean, like for example, something like a hinge. Okay, depending upon our view. So it's something like a hinge, except that a hinge is it has a different rotation of axis. But anyway, in this type of support reactions, then you can actually see the rotation. I mean, a large angle of rotation. For example, the wiper of an automobile. Okay, but that does not necessarily necessitates that you have a large that I mean that you must have a large rotation, because even though you only have, for example, you only have a few degrees of rotation, like for example a steel I-beam, and let's say this is a steel column. Okay, so the connection, there's one connection of this beam and column that's considered a pin, although we don't see, or we will not be able to appreciate the rotation. Okay, so this is our steel beam, and this is our column. Okay, so now if, or I guess I'd rather show you the textbook right here. Okay, so this textbook is a textbook by Timothy Philpott, and the book title is Mechanics of Materials. Okay, so right here there's a figure right here. So for example, in this figure, it says that this is a pin support. So this is what I was talking about, that this is the steel beam and this is the column, the steel column. And if the connection is along the web only, because for a steel I-beam, this one is referred to as the web, and this top and bottom portion, they are referred to as the flange. So if the connection is only along the web, then of course there is an allowance, or there is an accommodation of slight rotations. Okay, so if that's the connection, then that is idealized as a pin support. And right here, if we put a something like a slot that it is allowed to let's say to move along this let's say this x-axis, probably in terms, I mean probably because of temperature effects or things like that. Okay, so it is allowed to move, and if that's the case, it can be idealized as a roller support. Okay, so you don't see any rollers here, but the idea that you are allowing motion along this axis, then that's a roller. You're allowing motion plus you're allowing rotation, so that's a roller support. Okay, so this is one example of a roller support that you don't see any rollers. And right here, if it is totally I mean, if the flange and the web portion of the I-beam is totally fixed or restrained, then that's the time that it's idealized as a fixed support. Okay, so enough of the support reactions. We'll also have, by the way, we'll also have uh, terms like joints. Okay, so what's the difference between joints and supports? So usually supports are like the boundary conditions, or let's say for a beam. Okay, so this end, and that end, they're referred to as supports. But if we have a link, for example, okay, so if we have links like the slider crank mechanism in a mechanical systems, so this one is a support, right? But this one is a it's referred to as joints. Although in terms of reactions, they're almost they almost are the same. Okay, so we can have internal something like an internal hinge, or we can also have internal what else? Internal rollers or things like that. Okay, so that's it about the support reactions. Okay, and now we'll move on to the concept of equilibrium. So this concept of equilibrium is basically what it states is that um, the body is not in or there is no acceleration, right? There is no acceleration, right? There is no acceleration. Okay, so why is there no acceleration? Because the sum of the forces acting on the body, okay, forces and moments acting on the body is just equal to 0. Okay, so from the Newton's second law or Euler's equations of motion, summation of forces is equal to ma. So if this is 0, then if there is no resultant force, then there is no acceleration. Okay, so in terms of rectangular coordinate systems, just recall that we have summation of forces x is equal to 0, summation of forces y is equal to 0, summation of forces along the z is 0, and in terms of moment, okay, moment along x is equal to 0, moment along y is equal to 0, and moment along z is equal to 0. Okay, so if um, if we have a problem that can be solved sufficiently by the equilibrium equations, then the term there is we have a determinate uh, problems. So when you say determinate, it means that the equilibrium equations can solve the problem alone, or in terms of equations, that the number of unknowns is less than or equal to the number of independent equilibrium equations. Okay, so for 2D, right, this 6 right here, they are forces and moments in 3D, but for 2D systems, we only have summation of forces along x, summation of forces along y, and summation of forces along z. So for 2D systems, we only have 3 equilibrium equations. Okay, so if we have more unknowns, right? So if we have more unknowns than the number of the independent equilibrium equations, then that means we have an indeterminate problems. Okay, indeterminate problems, meaning that more or number of unknowns is greater than the number of independent equilibrium equations. Okay, so if that's the case, then we cannot be able to solve the problems purely by using equilibrium equations. So if that's the case, we need other equations. Okay, we need other equations coming from the geometry of deformation and what else? The force and deformation relationship, or other equations, force deformation relationships. Okay, so there are conditions already given in some texts about example beams, frames, or trusses. How do we know if the beam or the frames or the trusses are determinate or not? And it's also written in our um, lecture handouts. Okay, so for beams and frames, our condition is for 2D system is R is equal to 3n, or less than is equal to 3n. That is determinate. But if the reaction is greater than this 3 times n, this is indeterminate. Okay, and for trusses, the equation is b plus r be less than 2j. So if it is less than or equal to 2j, this is determinate. And if it is greater than, then that's indeterminate. So example right here. By the way, this R, this is the reactions. Okay, this is the reactions or support reactions. And this N is the number of members. Number of members. Okay, and right here, this one is the number of members for truss. And this one is number of reactions, number of support reactions, and this one is the number of joints. Okay, so example number 1, let's say we have a beam, we have a simply supported beam. Okay, so when we say simply supported beam, it's a type of beam that is that has a pin and roller support. Okay, and let's say this is our loadings. Okay, then how many support reactions do we have? Okay, so recall that for a pin we have 2, right? And for a roller we have 1. So that means that we have a reaction of 3, and right. So this is reaction of 3, and our number of member n. Okay, so this is just 1 member. So this is 1, right? So therefore, this is 3 is equal to 3 times 1. Okay, so therefore this is determinate. Right, so this is condition. Okay, so 3 is equal to 3, so therefore it is a determinate problem. Now, what if we have something like this, a fixed beam? Okay, so how many reactions for a fixed support? Okay, we have 3, right? So we have reactions along x, y, and a moment reaction along the z. Okay, so how many support reactions do we have? We have 6. And how many members, how many beam members do we have here? This is 1. So in other words, this is 6 is the number of unknowns is greater than the number of independent equilibrium equations. So this is indeterminate to the 3rd degree. Okay, 3rd degree. Okay, so you just simply subtract 3 from this 6 values. 6 minus 3, that's the number of the degree of indeterminacy. Okay, so the next here is, let's say we have something like this. We have a frame. Okay, so if we have this kind of frame, you would notice that we have 2 reactions right here, right? So this is 4, and the number of, if this is 1 member, then that's indeterminate. But if I put an internal hinge right here, so in this internal hinge there's gonna exist another reactions. So in total we have 1, 2, 3, 4, 5, 6. So we have 6 reactions. But for the number of members, so we have 1 member right here and another member in this side. So we have 3. We have 2 members. So that means we have 6 is equal to 3 times 2. So this becomes determinate. Okay, so that's one of the function of this internal joints, or of these joints, or this internal hinge, is sometimes it reduces the degree of indeterminacy, because that means that you can apply the equilibrium equations in this 1 member only, and you can also apply another equilibrium equations in this member. Okay, so that's why it becomes determinate. Okay, now for the truss. Okay, so let's say we have this truss. Okay, and this truss is, let's say we have a simply supported uh, truss. So in terms of equations, we have b plus r is greater than 2j. Now for truss, my technique is to think about the equilibrium equations applied in a joint, right? So if I apply the equilibrium equations in this joint, then how many equilibrium equations do we have? We only have two, right? Because we have summation of forces x along x and summation of forces along y, and the summation of moments does not come into play because there's no moment arm. Okay, so right here, how many support reactions? Okay, so we have three support reactions. So this is 3. Okay, plus, I mean, let's first count the number of members. So this is 1, 2, 3. So 3 plus the number of support reactions, 3, is equal to 2 times the number of joints. So how many joints? 1, 2, 3. So this is 6 equal to 6. And that means that this is a determinate problem. Okay, so um, that means that you can apply the equilibrium equations, the summation of forces x and y in this joint, then apply another equilibrium equation in this joint, and then apply another equilibrium equation in this joint. Okay, so that's why it is 2j. Okay, anyways, whether it's a beam or a truss or whatever structures, the main idea is the number of unknowns less than the number of available equilibrium equations. Okay, so because if it is more than, then it is statically indeterminate. Okay, so now let's move on to the topic about internal forces or internal forces. Okay, so the flow chart is that if we have this, for example, if we have this body right here. Okay, okay, so let's say we have an arbitrary body, but it has a regular shape. Now let's say we subject this body to external forces, right? So we have arbitrary forces. Okay, so let's write here external forces. Okay, and let's say this body is being supported by some supports. Let's say right here we have something like a roller support, and right here we have a pin support. Okay, so because of the external force, there's gonna be a support reactions, right? Okay, support reactions, and because of these support reactions, then there develops an internal forces. Okay, internal forces. Okay, so take note, the other one is external and this one is internal, which means that it is inside the material. So we usually do, or what we usually do in engineering is that we cut a section. So at this section is something like we do a samurai cut along this section. And what happened is that in this section, okay, so let's say this is our support. So in this section, there's actually internal forces acting, right? By the way, this is not the exact distribution of the forces, but rather what I'm just showing right here is in this section we see internal forces, and we can only see it if we use a special glasses that can see through the sections. Okay, so by default, right? By default, when we're dealing with 3D systems or 3D structures, by default, what we have is, right, so what we have here, let's say this is our x, this is our y, this is our z. what we have is we'll have a force along the y direction. We'll also have force along the x direction. We'll also have force along the z direction. Okay, so that's the default. And we can also have something like a moment. We can also have moments in the x and y, x, y, z directions. Okay, so that's the default. Now, if we are just dealing with two-dimensional systems, then by default we have this internal forces. So we have this specifically denoted as P, or sometimes they use N, and right here, or let's say along this. Anyway, the direction could be downward or upward, but along the y direction. And we can also have a moment along the z direction. Okay, so this one is P, this one is M, and this one is V. Okay, so these internal forces, this is termed as axial force, and let's write internal. And this one is internal moment, and this one is internal shear. And there's also another one right here. This is internal torque. That's the specific term if we are referring to the rotation that produces rotation along the longitudinal axis. Okay, so here the longitudinal axis is our x. So this is internal torque, internal moments, internal axial force, and internal shear. Okay, so depending upon the type of structures or the type of members, not everyone right here is present. Like for example, for trusses. Okay, so axial members or axial forces only, axial only. This is common for truss members. What else? Braces, cables, right? Cables and columns, for example. Although sometimes columns, they have moments plus axial. Okay, so let's say moments plus axial. So it can be sometimes columns. And we can also have, like for example, moments and shear. Moments plus shear. So example of moments plus shear or beams. And sometimes we have moments plus shear plus axial. Right? So if we have three internal forces, these are typical for analysis of frames. Okay, so the point right here is that because of external forces, there's going to be an internal force, and this internal force could be internal moment, axial force, or internal shear or torque. Okay, so and depending upon the type of structures, let's say if you're a truss member or a column or a beams or frames, then not everyone or not all internal forces are present. Okay, so sometimes we want to present these axial forces. These internal forces in terms of a graph. Okay, so for example, we have a beam. Right. Okay, so we have a beam right here. Okay, that's under this uniformly distributed loads, and recall that for beams, the internal force that's present is the shear and the moment. Okay, so for this specific type of boundary conditions or support conditions and external loadings, the shear diagram for this is something like this. Okay, and for the moment diagram, it's something like this. So what that means is that at any length or at any point along this length, then there's actually a varying magnitude of the shear. So near the supports we have a maximum shear, but at the midspan we have a zero shear. But in terms of moment, we have a maximum shear at this distance. So the point right here is that these internal loads, they are sometimes represented by this diagram, and this diagram, they are termed as the internal load diagram. Okay, and for example, another one is for axial. So let's say we have this bars that's being subjected to, let's say, to this force from at this point, and right here it's subjected to another force, and right here subjected to this force. So we have three forces, and what if we want only to we want to graph the internal axial loads? Okay, so if that's the case, then it can be represented by a graph. So right here probably it's like this, and then from this section it's going to like this and like that. Okay, so this is just an example. Okay, so that means it's something like a visual way of seeing the magnitude of the internal forces. Okay, so in the next video we'll be doing sample problems regarding the support reactions, the equilibrium equations, and these internal forces. All right, so see you in the next video.